to be honest. And a mud rock is what it says it is. It's a rock that before it became lithified, before it became a rock, it was mud. So that's the grain size term, and it's made of clay minerals. And clay minerals are aluminosilicates. Now that should be ringing a bell, because you last heard it related to feldspars. So aluminium, Sr, silicon and oxygen. But these clays are hydrated. Clays have the OH in the lattice. And indeed, if you leave feldspars on the surface of the planet and let them weather, and Andrew will be mentioning this as well, they will convert to clay. And China clay is a very pure form of altered feldspars. Okay, so it's no surprise that we get a lot of mud rocks, because we have a lot of feldspars in igneous rocks. And also quartz. Quartz doesn't weather to anything else or erode. When it's eroded, it just breaks down to smaller quartz. And so quartz is quartz, but on the surface of the earth it will gradually become smaller in grain size as it erodes mechanically. And also it will become more rounded usually, because it doesn't tend to break up very easily. It just rounds, it polishes. So you have mud rocks, which are mainly clays, i.e. wet minerals, and you have sandstones, which are most commonly quartz, because quartz is the most robust mineral on the surface of the earth. It's the mineral that lasts the longest because of its physical properties. Carbonates are the chemical precipitates. Although they can be formed of broken up bits of shells and things like that, they can be directly precipitated as well. And they are calcium and carbonate. Okay, calcium carbonate ions. So those are the three main categories that we're going to mention and that Andrew will mention. And just something here, sedimentary rocks on continents cover a far wider range than they do on ocean crust. So on continents, sedimentary rocks, we found sedimentary rocks, obviously, that they're forming today. The sand on the beach today can easily become a sandstone. Okay, the rocks are forming all the time. We haven't stopped. And we have dated sedimentary rocks that are, 4,000 million years old, 4 gigayears old. So continental crust has this process of forming sedimentary rocks from other rocks has been going on for 4,000 million years, or 4 gigayears. And as the planet is only 4.6, say, gigayears old, that's a long time. And don't forget, sedimentary rocks can be formed from fragments from igneous or sedimentary or metamorphic rocks. It can just keep going on and on and on and on. It can get quite complicated if you think about it. It's like an Escher drawing. Now, I am going to go down one and just look at this section here. I don't expect you to understand this. This is an interpreted seismic section of the Atlantic coast of North America. And really it should be, so this is North America. Okay, so this is distance horizontally from the land to the ocean. And this is kilometers depth, and it's a cross section. And this has been interpreted from seismic waves. This is geophysics. Now, the continental crust here, this is the granitic stuff, which has got lots of faulting in it, and that faulting is actually going down to this lovely little rift valley, and this would be the edge of the continent. When it was rifting, it was thinning and rifting, and the other part of the continent will be over there. And then you have the ocean crust glued on it, okay? And this will be all mafic, this will be all basaltic, all of the green will be basaltic, and all of this sort of pale creamy colour will be granitic. We've had a bit of volcanism. These are evaporites. This is where, evaporites forming today in salt lakes. And we've got a deceased, a fossil coral reef here. So this is carbonate. And then we've got various aged sedimentary cover, which will be a combination of mud rock and sandstones. Okay, so you can see a typical profile of the crust. So we have continental crust joining oceanic crust, and across both of them we have younger sedimentary material. Okay. Now, this is based, by the way, as it says here, on gravity, magnetics and seismics. It's just to show you, give you some idea of the relationship between these things. And this is somewhere I want to visit in Japan. I tell you, I don't show you my holiday snaps. I show you photos of where I'd like to go on holiday most of the time. These are people for scale. And this is a cutting, that's a bench in a quarry. And this is a beautiful exposure of the sedimentary rock formed in a trench, in a subducting trench. This is the chunks of rock. These are marine sediments, some carbonates in here, some mud rocks that have just dropped off the side of the cliffs of the trench. Don't forget, these things go down 4 kilometres below the abyssal plain, so they're up to 9 kilometres below the surface of the ocean, right? They're huge things. And these lumps just drop off and go to the bottom, and then they can get plastered on the continental crust or the other plate that they're accreting against, and that's what's happened here. We've got these huge blocks. We've also got lovely, we call them, wait for it, Swiss roll structures. Geologists are fixated on food, where you get rock that's actually rolled up like a carpet. It must have been quite plastic, i.e. viscous, but still runny enough, so as the rock was falling down, it was rolling up. And look, there's more of these rolls here. A stupendous place, which I really must go to in Japan. It's a fossil trench area in the Japanese subduction zone, to show you a large-scale fragment in a sedimentary rock. Next, we have the quiz, which the first group got to, the first lecture got to, and those people who were still alive and who could answer it, answered it correctly, which is this one. And that's the summary slide. And I'm not going to go all over this because this is summarising the last 2 lectures. Okay, questions, put them on the lecture question side on LMS.